Unit 4. In this video, we're going to talk about learning target 4E, which is about integration by parts. So integration by parts is another technique of integration, and it is used to undo the product rule for derivatives, and is generally used when we have a product of two functions inside the integrand. So we've already learned about what our basic integrals are and how to do U substitution. Those are still always going to be our first things that we want to try. We always want to first identify, well, do I have a basic integral or not? If it's a basic integral, then we should know the antiderivative. Now, if it's not, we want to think about if a U substitution could work, because a lot of integrals can actually be done from U substitution. But there are cases where we have integrals where U substitution will not work, and that's where our other techniques of integration are going to come into play. And so this next technique that we're going to learn after U substitution is called integration by parts. So how exactly does integration by parts undo the product rule? Let's consider the product rule for derivatives, which I have shown below here. So if I take the derivative of f of x times g of x by the product rule, that's equal to f prime times g plus f times g prime. Well, I have an equation here, and I can integrate both sides of that equation, and it will still keep the equation balanced. So I'm going to integrate the derivative side, and then that will be equal to the integral of what we get out from the product rule. We know from prior sections in this unit that if I take an integral of a derivative by the fundamental theorem of calculus, those two operations undo each other, and I just get left with the original integrand, which would be f of x times g of x. And that if I have the sum inside of an integrand, I can actually break that apart as the integral of the first term plus the integral of the second term. From here, I'm going to do a little rearranging. I'm going to actually subtract over this integral of f prime times g to get this integral of f of x times g prime of x dx by itself. Then from our third line down to our fourth line, I just flipped it. So I moved the integral of f of x times g prime to the left side over here, equals still our f of x times g of x minus the other thing I did do was I flip-flopped the f prime times the g inside my integrand. And we're allowed to do that because multiplication is commutative. Now the reason I set it up this way is because this identically matches up with our integration by parts setup. So integration by parts for indefinite integrals tells me if I'm integrating a function u times dv, that is equal to u times v minus the integral of v du. You're probably thinking, well, why the heck does that work? That works using the product rule, which is what we just shown above. And let's see how these pieces all get interconnected. So up above, I used f of x times g of x, since we're used to that from our product rule, but I could rename these functions. And what's happening here is I'm renaming u to be f of x, and I'm actually renaming our v to be g of x. What that would tell me then is that my du would have to be equal to my f prime of x dx, and that my dv, when I take the derivative there, would be equal to g prime of x dx. And we're just renaming stuff. So in my first integral, since I have f of x times g prime of x dx, that's equivalent to my u for my f of x, and then g prime of x dx is equal to this dv. And that matches up with what we have on the left side down here in our integration by parts equation. Now that will be equal to, we know that that's equal to f times g, well that's our u times v, which we already have, minus the integral of g, we renamed as v, and f prime of x dx is equal to du, and that matches up with our last integral down here. Now usually integration by parts formulas use this u and the v because it's a little bit easier, it's less cumbersome to see than having to have f of x and f prime of x and g of x and g prime of x. But technically this also works as an integration by parts formula on this last line as well. So what integration by parts tells us is that if I have the integral of two products, and it works out that I have this f times this g prime, I can actually break that apart using the product rule, using our product rule like we did here. Now I'm not applying the product rule for derivatives at all, but I'm using that equation that we had to break this apart. So the integral of u times dv is equal to u times v minus the integral of v du. And from here, I would actually have to keep integrating. But what's nice about the integration by parts formula is that if we've set it up correctly, the integral of v du, which is left over, is really easy to integrate. And this would either be a basic integral or a U substitution integral that we could do. The issue is that when we start off with the integral of u times dv, there is no way to do a U substitution. This is not a basic integral. And so through the integration by parts formula, we can rewrite it so that we have u times v, which is outside the integral, minus the integral of v du, and then this integral of v du is really much easier to take. And if we've set up the integration by parts formula correctly, this will be a nice integral for us. If it becomes a more complicated integral, then we have to recheck what we set up for our integration by parts. So before we integrate it all, we actually have to identify what our u is and what our dv is. So down below, I have this table set up for us to look at. And what we have here is I have u equals on the left and then the du directly underneath that. Remember, we get to choose what our u is since that's starting off in our original integrand. And to get to du, I would be differentiating. This is the same thing as when I started with f, and to get to f prime, I took a derivative. Then we also get to choose what dv is, since that's in our original integrand. So we choose the dv down here, and then to work backwards and to get back to what v is equal to, we would anti-differentiate or we would integrate. So we always want to make sure our table is set up this way. That way we can use what I call our lucky 7. Now our lucky 7 is something that I learned from my college professor, and it's a way to help you, instead of having to memorize this integration by parts formula, which can get very confusing, and u and v are very similar, and if we accidentally miswrite something, we would have a major issue. If we set up this table down below with u and then du underneath it, and then v on the same line as u, and dv underneath that, we can use this lucky 7 to help us get this equation. So in our integration by parts formula, the first thing I have is u times v. So I would multiply directly across and go u times v minus the integral of v times du, which would be our v times our du. This cross here kind of starts to look like a 7 since I multiply directly across and then I multiply diagonally. So I have u times v minus the integral of v du. Now over the years as I've taught this, I've had some classes that have gotten a little bit more creative with it, and instead of having a straight line down, they'll say, well, what if we curve that since we're going to integrate that? So u times v minus the integral of v du, and then some people write their 7s with that slash through it, so other students have said, well, let's put a slash through that diagonal line to represent that we're subtracting, and that makes it look like a 7 even more. So we have u times v minus the integral of v du. And this is just a way to help us really set it up versus trying to memorize this integration by parts equation every single time. And again, it's important. We get to choose the u and we choose the dv. And then to get the du, we would take a derivative. And to get the v, we would take an antiderivative. And sometimes this antiderivative step might involve a little U substitution, or it might be a basic integral. It just depends on what the problem is. So since we get to choose these pieces, we want to make sure that our u is easy to take a derivative of, and our dv should be easy to integrate. So below, what we have is kind of the order for picking our u function. And so that first step that I would want to pick is if I have a log, that would be my first choice for what my u should be equal to. Now, if I don't have a log, but I have an inverse trig function, then that would be my u. If I don't have a log and I don't have an inverse trig, then my third choice there would be an algebraic expression or a polynomial. If I don't have a log, an inverse trig, or an algebraic expression, then my fourth choice would be an exponential function. And if I don't have any of the above, but I have a trig value or a trig function like sine, cosine, tangent, something along those lines, I would pick that to be my u. Now, a couple years ago, I had a class that helped come up with an acronym for this. So we have logs, inverse trig, algebraic, exponential, and then trig functions. So LIAET, they came up with the phrasing, Lucy is always eating tacos. If that helps you remember the order, I think it's definitely helpful if you want to come up with your own saying for it. We just want to make sure we're doing logs, inverse trig, algebraic, exponential, and then regular trig functions from there. So let's look at some examples to go with this. And I'm going to leave that integration by parts set up top for us. So in this first example, we have the integral of x times sine of x dx. Now let's look at this. This is not a basic integral since I don't just have x or I don't just have sine of x. I do have a product here. I could try to do a U substitution, but we know that when I do a U substitution with a trig value, since I only have one trig function that's sine, my U substitution would want to be the input to my sine. Well, if I make my U that x value, that doesn't make this x in front go away. It would just rename that to be U. And so when we had all of our U substitution examples, our powers inside the trig function were always bigger than our powers that were out front. And in this case, if my powers are the same, then U substitution is not going to work because in that U sub, when I find my du, I'm dropping down a power in my derivative, and that's why we always have the higher power inside and the lower power outside, since again, U substitution is undoing that chain rule. So here we have to try another technique of integration, so we're going to try our integration by parts. Now in this equation I have two functions. I have the x and times the sine of x, and I have to figure out which one is my u and which one is my dv. Well, this is where that phrase, Lucy is always eating tacos, can come into play. So I don't have any logs, so that won't be here. I don't have any inverse trig functions, I just have a sine, so a regular trig function. Algebraic expressions, those are our polynomials, that I do have. My algebraic expression that I have here is that x. So I'm going to go ahead and make x my u, which means that this sine of x dx has to be my dv. So I've now started to set up this table. To get from u to du, I'm going to take a derivative. So the derivative of x would give us 1 dx. And then to get from dv to v, I'm going to take an antiderivative, or I'm going to integrate. Now the integral of sine is a basic integral, and we know that the integral of sine is negative cosine. And you can always check these because the derivative of cosine is negative sine, but then this negative out front ends up giving me that positive sine value. So now that we have our table set up, I can go ahead and use that lucky 7. So it would be u times v. So I'm going to write this out below. So we're taking that original integral, which was x times sine of x dx, and this will be equal to u times v, which is x times negative cosine of x, minus the integral of v du. So minus our integral of the v function, which is negative cosine of x, times that du, which is 1 dx, so that is just going to be dx. Oops, I forgot to close that parentheses there. So if we've set up our table correctly, I always multiply directly across in the top row for u times v, which is our x times negative cosine of x, minus the integral of v du down the diagonal. And that green right there is making our lucky 7 per se. Now from here, this is equal to the original integral that we had. If I clean this up a little bit, I'm looking at negative x times cosine of x. Now the double negative here would actually become a positive, so plus the integral of cosine of x dx. Well, I don't integrate this negative x times cosine of x. It's no longer inside the integral, but I do integrate the cosine of x. Cosine of x is a basic integral, so this integral is much nicer to deal with than the original integral that we started with. And if we've set up integration by parts correctly, that will always happen. So our final answer here will be negative x times cosine of x, and then we know that the integral of cosine is equal to positive sine. So I get plus sine of x, and since this is an indefinite integral, I have my plus c, since I don't have any bounds, so it's not possible to determine that constant of integration. So here's our first example with integration by parts. The trickiest part of this is making sure that you're setting up your table correctly. And if you flip-flop your u and your dv, when you get down to the step of having u times v minus the integral of v du, this integral would be really challenging to take. It would actually be worse than the original problem that we started with. So that's always a good way to check that you've set up the correct integration by parts table. And if it becomes messier, then scratch that off and try it again. Flip-flop what you thought your U and your dv is, and then that will help you solve it through there. But this is also where we can use the saying of Lucy is always eating tacos to help us pick our U. So this is what our U would be equal to in the order in which we'd have it. So if I ever have a log or a natural log, that has to be my U. And if there's no log or natural log, but there's an inverse trig, then that would have to be my U, and so on down the table. So since I had an algebraic expression here and a trig function, algebraic expressions come before trig functions, so that's why my U was equal to that x. Let's look at our second example here. So here we have the integral of 12x times e to the x dx. Now this 12 is just a scalar or coefficient on the integral. You could take it out of the integral, but I'm going to go ahead and just lump it together with the x so that I don't have to worry about multiplying through by something at the end of my answer. But if you would like to, we could take the 12 out and then just make sure you've got a lot of things in parentheses and you'll end up distributing. So our job here is to integrate this guy. Well, if I try to do a U substitution, because that should always be the first thing I try, I have an issue here. If I'm going to U sub with an e to something, then my U would have to be my exponent. But if my U is equal to x, there's no way to get rid of the x in front. Again, this is a similar issue to what we had in example 1, where the powers of what my inside function is and my outside function are the same, so there's no way to do a U substitution here. So we're going to try an integration by parts. Why don't you guys pause the video and decide what your U is equal to and what your dv is equal to. So using that phrase, Lucy is always eating tacos, I have no logs, I have no inverse trig, but I do have an algebraic expression, which would be the 12x. So that U is going to be equal to the 12x, which leaves the e to the x dx to be our dv. From here, I have to find the remaining pieces before I can multiply through and use our lucky number 7. So why don't you guys figure out what your du is and what your v is. So to get our du, I would take a derivative. So the derivative of 12x is going to be 12 dx. And to get from dv to v, I want to integrate, or I want to take an antiderivative, and the integral of e to the x is just e to the x. Now from here, I can set up that lucky number 7 to get what our original integral is equal to. So we're starting off with the integral of 12x e to the x dx. Using integration by parts and our lucky number 7, why don't you set up what this would be equal to? So what we would have is our u times v, so I'll get that 12x times e to the x minus the integral of u times dv, which would be our e to the x times that 12 dx. So I have u times v, 12x times e to the x, minus the integral of v times du, which would be e to the x times that 12 dx. If we clean this up and make this a little bit nicer, we have 12x e to the x minus the integral of just 12 e to the x dx. And if you want to take that 12 out, you could take the 12 out of the integral as well. Now that I'm looking at this, I don't need to integrate the 12x e to the x, that's outside the integrand, but I do need to integrate this 12 times e to the x. Well, this is actually a basic integral, so this is a lot nicer than the integral that we started with, so we did do our integration by parts table correctly. So I get 12x e to the x minus, well, 12 is going along for the ride, and the integral of e to the x is just going to be e to the x, and then since I have an indefinite integral, I get our plus c. And that will be our final answer for that one. Let's look at another example, and this one's going to have a natural log in it. So in our third example here, we have the integral of 7x times the natural log of x dx. Well, this is not a basic integral since I have a product of functions here. I could try to do a U substitution, and we know that anytime I have a natural log, if a U substitution is going to work, then my U has to be equal to the natural log of x. And if I were to make my U equal to the natural log of x, then my du would be 1 over x, and I have no way to get rid of this x that's being multiplied. If that x was being divided, then this would actually be a U substitution problem. But since I have the x times the natural log, there is no way to get a U sub to work. So our next technique of integration that we have, integration by parts. So we're going to have to set up our integration by parts table. Remember, we get to choose the U and the dv. And remember that phrase, Lucy is always eating tacos. Why don't you guys pause the video and decide what your U is going to be equal to and what your dv will be equal to. Well, in that phrase, the first one is L, which stands for log, so that means my U has to be equal to natural log of x, and my dv then has to be the remaining stuff, which would be the 7x dx. Now that 7, if you want to take it out of the integrand, you can. You can take scalars out of integrals, but then I'd have to multiply through by 7 at the end, so instead I'm just going to keep it attached to the x. Now that we have our u and our dv chosen, why don't you guys find your du and then find your v. So to get our du, we would differentiate. Derivative of natural log is 1 over x dx. And if we want to go from dv to v, we're going to integrate or anti-differentiate. And the integral of 7x would give us 7x squared over 2 by using the power rule. So now we're going to take our original integral, which is the integral of 7x times the natural log of x dx, and we want to set this up using integration by parts. So that's where our lucky 7 is going to come into play. Why don't you guys pause the video and set up what this original integral would be equal to using our lucky number 7. So that lucky number 7 tells me that I get u times v, so I get natural log of x times this 7 over 2 x squared minus the integral of v times du, which would be 7 over 2 x squared times 1 over x dx. So our u times v minus the integral of v times du. Now that looks kind of messy as it stands right now, so let's clean this up. And we're going to have 7 halves x squared times the natural log of x minus, I can pull the 7 halves out of the integral. So 7 halves the integral, well, x squared times 1 over x, I have the same base, so I get an x that cancels, and I just get left with x dx. Well, that looks a lot nicer than what I had to begin with, especially when I had that natural log. And so here, I can actually just use a power rule since the integral of x is a basic integral. And I would end up with 7 over 2 x squared times the natural log of x minus 7 halves times the integral of x would be x squared over 2 plus c, since I have an indefinite integral. And that would be our final answer here. So our goal with integration by parts is to get down to an easier integral that is much easier to evaluate. And when I have that natural log inside my integrand, there's actually no way to integrate ln of x. So if I were to make my dv equal to ln of x, I'd have to integrate it. And to integrate ln of x, it's actually an integration by parts problem in and of itself. And it's an example that we're actually going to look at in class and try together. So that's why in that choosing of that u saying of Lucy is always eating tacos, that's why our natural log is always the first thing we would choose to be u, because there is no way to integrate it without doing its own integration by parts problem there. So in these first 3 examples, we've kind of seen how we can have a bunch of different products of functions to try. U substitution didn't work on any of them. None of them were basic integrals, so we tried an integration by parts that ended up working. Let's look at our 4th example here. And then we're going to look at some definite integral examples. Well, in this fourth example, I realize I'm missing the integral sign, so there's a typo there. There should be an integral sign there. So I have the integral of x squared times cosine of 3x dx, and I'm going to want to go ahead and do integration by parts. If I think about trying a u sub, because that should always really be in the back of my mind, my u would have to be this 3x, but then there's no way to get the x squared replaced. And if I were to make the u equal to the x squared, then I would end up with a u times cosine with a dx inside. That's just not possible. Anytime I have a trig function, if I'm going to do a u sub, u has to be the input function here. And so since the power of what's inside the trig function is smaller than the power outside, a U sub is not going to work. Just like in our first example, when I had an x and an x with a sine function, a U sub didn't work. So U subs only work if the power inside is bigger than the power that is outside. So let's do an integration by parts. We have to choose our U and our dv. Why don't you guys pause the video right now and decide on what U would equal and what dv would equal. So in that phrasing, I have no logs, I have no inverse trig, but I do have an algebraic expression. That would be the x squared. So my U is going to be equal to x squared, which means that cosine of 3x dx is going to be our dv. Now from here, why don't you guys differentiate U to get du, and then why don't you guys integrate or anti-differentiate dv to get our v value. So to take the derivative of U, I'd get 2x dx, but then to take the antiderivative of cosine of 3x, there's actually a little baby U substitution going on here. So on the side, if I were to write this out, I'm ultimately integrating cosine of 3x dx, which allows me to pick up a 1/3 coefficient if I were to U sub on the 3x. So when I integrate cosine of 3x, I get 1/3 sine of 3x. So there are integration by parts problems that have U subs inside of them when you're finding the antiderivative in your table setup. So we want to make sure that we're being careful, and usually it's just a little what I call a baby U substitution where it's just picking up a constant term, but we don't want to forget about that 1/3 because that will make a huge difference in our final answer. From here, I can now set up my integration by parts. So I'm starting off with the integral of x squared times cosine of 3x dx. Using our lucky number 7, set up what this would be equal to. So our lucky number 7 tells us that we get U times V. So we get x squared times this 1/3 sine of 3x minus the integral of V times du. So that would be 1/3 sine of 3x times this 2x dx. So we've set up our integration by parts. I'm going to clean this up because it looks a little bit messy. So I have 1/3 x squared times sine of x, or sine of 3x, that's all outside the integral, minus the integral of, I can multiply the 2 and the 1/3 to get 2/3 x sine of 3x dx. Well, this integral looks nicer. I don't have an x squared anymore, but I still have an x times a sine. So this is not a basic integral yet. A U substitution won't work for the same reasoning as before. The power inside the trig function is equal to the power outside. So what do you guys think we have to do to integrate this problem? We set up the table correctly because the integral got a little bit easier, but it's not quite there yet. What do you guys think we'd have to do? We actually have to use integration by parts again. So I'm going to set up another integration by parts table over here on the right that will help us integrate that function. So I have to choose my U, and then I have to choose my dv. Well, looking at this, what do you guys think our U will be equal to for this integral, and what do you think our dv will be? So I have no logs, no inverse trig, but I do have an algebraic expression that would be the 2/3 x, which means that the sine of 3x dx is going to be our dv then. Well, I can take the derivative and I'll get 2/3 times dx. I can take the antiderivative of sine of 3x, that is going to give me another little baby U sub with the 1/3, and I'll actually get negative 1/3 cosine of 3x, since the integral of sine is negative cosine. And then the 1/3 is coming from our little baby U sub. Well, from here, this first piece doesn't change. This 1/3 x squared times sine of 3x, that's unaffected. That's not part of the integral, so that's still part of my final answer. I still have the minus sign, but I'm going to put parentheses here because I'm going to have a whole nother integration by parts that gets set up for this integral that we had in our second line. Why don't you guys pause the video and set up that integration by parts using your lucky number 7 on our new table that we have to the right. So using that, I would get u times v. So I'm going to get 2/3 x times negative 1/3 cosine of 3x. So 2/3 x times negative 1/3 cosine of 3x minus the integral of v times du, which would give us another negative 1/3 cosine of 3x times 2/3 dx. And then I want to close those parentheses because that negative sign in front actually needs to get multiplied into everything. So there's our integration by parts setup. The second time, u times v minus the integral of v du. This first term stays the same. It's already outside of the integrand. And on this second term here, if I distribute that negative sign in, I'll have a negative times a negative, so I'll end up with a positive. Then 2/3 times a third is going to give me 2/9. I have x times cosine of 3x. And when I distribute the negative sign in here, I have the negative that's out front, the negative that's in front of the integral, and the negative 1/3. 3 negatives multiplied together is going to still keep this negative. So I have negative and then 1/3 times 2/3, so negative 2/9, the integral of cosine of 3x dx. So lots of kind of cleaning up there with multiplying stuff out. I still do need to integrate this last function. I'm going to rewrite my first two terms. And then on that last integral, that is much nicer than what we had to begin with. Since we're just integrating cosine of 3x, that will be another little baby u substitution where we pick up a 1/3. And we know that the integral of cosine is positive sine, so we end up with sine of 3x plus c. So this time, since we did integration by parts twice, we actually ended up with 3 terms, since our second term turned into 2 more terms when we did the integration by parts on that. So our whole final answer down here is this whole mess, and then don't forget that plus c that we have on there since we don't have any bounds. Now from here, I could have actually said at the beginning that I would have to do integration by parts twice. Anything that we notice about the original integral here that might signify having to do integration by parts more than once. So what I notice is that x squared. And so because I'm starting off with an x squared, that's my algebraic expression, so that becomes my u. When I take a derivative there, I still have an x, versus in all the other first 3 examples, when I took the derivative of u there, it knocked down to be an x to the first power, basically. But because I started with an x squared here, I knew that that was going to lead to another integration by parts table once we set up the first one. And that can happen. If I had an x cubed here, I'd actually have to do this 3 times. And we're going to notice some trends like that happen just because of how derivatives work on how you're knocking down powers every time you take a derivative. Okay, let's look at one more example that we have. And this is going to deal with what happens with integration by parts if I have bounds. Well, nothing changes except for instead of putting plus c, I have to evaluate the integrals. So I still have the integral of u dv equals u times v minus the integral of v du. What we don't want to forget about is the fact that we have to evaluate the bounds on that u times v. Although we never integrate that and it comes out of the integral, we still have to evaluate it because if I'm integrating and I have bounds, my final answer has to be a number. I don't need to simplify that number, but I do need a numeric answer. And if I just left the u times v alone without subbing in anything, and then there's x's, then I don't have a number as my final answer. But how we set it up will all be the same. So in example 5, we have the integral from 1 to 4 of negative x times e to the 2x dx. Why don't you guys pause the video right now and decide on what your u is and what your dv is. So here I have no logs, no inverse trig, but I do have an algebraic expression. That will be the negative x, which leaves the e to the 2x dx to be my dv. Now I didn't discuss it at the start, but a u sub won't work here since the power in the exponent is equal to the power out front. So there's no way to do a u sub, and this is not a basic integral since I have x times the e to the x. From here, to get our du, we're going to differentiate, and to get our v, we're going to need to integrate. why don't you guys pause the video and find your du and your v. So to get our du, if I take a derivative, I'll get negative 1 times dx. And then to get our v, I need to integrate. Well, if I integrate e to the 2x, that's another little baby u sub. So we're picking up a 1/2 e to the 2x. And that's happening, if I write it up top here, because I do need to do a little u sub here with that 2x. But that's just a scalar that we're picking up, so that's why we get that 1/2 then in front of our integral. So our original problem, we've got integral from 1 to 4 of negative x e to the 2x dx. Well, we can now set up integration by parts using our lucky number 7. So why don't you guys set up what this integral would be equal to, and then we'll check it together. So this integral would start off by doing u times v. So I would get negative x times 1/2 e to the 2x. Because I have bounds now, I need to technically evaluate this from 1 to 4 minus the integral of v times du. So that would be 1/2 e to the 2x, well, times a negative 1. So what if I make that a negative 1/2 then, and then the dx is on there. And then this also needs to keep our bounds from 1 to 4 as well. From here, let's integrate before I sub in the bounds. So I'm going to just rewrite this first expression, negative 1/2 x e to the 2x. We will eventually evaluate it from 1 to 4. Then I get plus 1/2. The integral of e to the 2x is another little u sub, so I'm picking up another 1/2 e to the 2x evaluated from 1 to 4. Now from here, there's a couple options to continue. We can evaluate each of these terms separately, or since they have the same bounds from 1 to 4, I'm going to group these together and put the bounds all at the end for both of these expressions. So I'm going to evaluate from 1 to 4 into both of these. Now we know that we sub in our top bound first, so I get negative 1/2 times 4 e to the 8th plus 1/4 times e to the 8th, since I get that 2 times 4, minus, now I have to sub in my lower bound, which will give me negative 1/2 e to the 2nd plus 1/4 e to the 2nd, and I want to make sure that I have parentheses around it since they're both being subtracted. And that will actually be our final answer then. Let me see if I can box that whole thing. There we go. So even when we do integration by parts with bounds, it's the same process. We then just have to do that additional step of subbing in the bounds at the end, just like we've done with all of our other definite integrals that we've had. The tricky part is to remember, though, that that first piece does get this evaluation bar from 1 to 4. We want to make sure that we have that notation on there, one, to remind us, but also because that piece gets evaluated. And it wouldn't make sense to just at the end start evaluating it if I didn't first have this evaluation bar from 1 to 4 on there. So in this video, we went through quite a few integration by parts examples, and we'll continue to practice more in class.